Hey, good morning. Um, so first, let me quick attendance check. Um, and while I'm doing that, a couple things to remind you of. So as we're getting close to the end of the semester, um, we need to make sure um, that we're getting ready for the final project. There was a big announcement about that um, last week, kind of laying out what it's really going to be about, but make sure that you take a look at that and decide what do you think you want your presentation to be. What I want to happen is um, for everyone to contact me by the end of this week so I can just make sure that both you and I have an idea of what your presentation is actually going to be. Um, if you have an idea, I'll be happy to talk about it with you. If you're looking for some ideas, there were some posted in that announcement. But besides making sure you're thinking about it, I want to make sure that your ideas aren't overly broad. So I wanted to talk about something like I don't know, some of the examples I gave is something like talk about geometry. That's a really good topic. There's a lot of interesting things to say there, but that topic on its own is way too broad. Or something like you want to talk about the philosophy of math if you're um, into philosophy at all. That's also a really interesting topic, but that on its own is way too broad. So how the sort of email discussing your topic will likely go is you'll contact me with some idea. I'll say, great, sounds like a good topic. Let's talk about more specifically what your talk will be focused on. And if you have some ideas, then you can mention those. If I can, or if you don't propose any specific things, I'll say, here are some ideas that I have. So I want to make sure that your talk is focused a little bit, so you really have an idea of what you want to research, and you're not just doing a lot of stuff really shallowly, but you have that's narrow enough that you can kind of get in depth a little bit. Also, I want to make sure that your topic has enough to talk about. So something like one thing, I don't know if I put it in there, but voting theory is kind of interesting topic. And connected with voting theory is something like the electoral college, how the United States chooses its presidents. That's really interesting and very specific, but also your talk can't just be, let me tell you what the electoral college is and how we choose a president. So just kind of giving a definition of a thing that involves numbers, that's not really enough either. There should be a little bit more to it. So, I mean, the Electoral College, and this is an option if you're interested in politics. There are things like how can it what are some pros and cons of it? Why was it chosen? So a little bit of the history, how it changes over time, um, because it's based on populations, um, and what are some kind of drawbacks to it? Why is it maybe not the best, or what are maybe better ways of voting? So it really is open, and if you need some ideas, I'm happy to give you those. But whatever idea we come up with is, um, we'll want to make sure that it is something that you can give a informative kind of mathematical talk um, about. Okay. So if you have any other questions, I'll be happy to answer those. I think after class or by email. Um, let's keep going. Also, something that would be good to contact me about is there's going to be some homework assignments continuing to show up. Not too many because we're almost done this semester, but some of them are going to be make or find the trend line for some data. So using these spreadsheets to make the approximating line or curve of some different type. If that is going to be an issue as far as like software, please be in contact with me. I'm using Excel, but if you have access to any spreadsheet software, even I think, I'm not sure, there might be like Microsoft Office available through Piedmont, or there might be some online spreadsheet. But if you have technology kind of concerns, let me know soon, so we can start talking about how you can do those kinds of problems in the best approximation possible with the technology that you have in hand. So what we've been talking about, and we'll kind of wrap this up a little bit in a little bit today. We were talking about, so we had been talking about finding linear models, but the real case where you want to find models is you're given data that maybe doesn't exactly fall on the line. And we want to think about how can we find a function? So given these 2 points, the 10,500 and the 14,800, we can find a line that goes through them, but that doesn't exactly fit all the other points. So we want to think about what are other ways of finding a line which approximates the points that we're given. And so this line is produced by Excel. There's a formula in there finding this trend line. The formula is pretty close to the formula we had going through 2 points, which says that was, we weren't too bad just picking 2 points and making the line through it. That's not always the case. But what this line is doing is that it's trying to find a single line. So it's maybe, in this case, doesn't actually go through any of the points. But if you look at the kind of total error, so looking at the distances from the line to each of the points it's trying to approximate, the sum of all of those distances and the total error is as small as possible. And so there's a formula for it that we're not worrying about, but we can kind of see that's what it's trying to do. By being a little bit below all of these points, it's able to be closer to this point than if it was higher up. And so that balancing act of saying, look at all the points, and we want to simultaneously minimize the distance to all of them. So we can find a line. Excel or whatever spreadsheet software you have provides the formula for you. It also provides this R squared, which is a measure of how well your line approximates the points. R goes from 1, meaning it exactly goes through all of the points, and 0, which means it essentially doesn't approximate them at all. But as we're coming up with these trend lines, and I showed this picture last time, here are 4 different data sets that all have the same, or at least essentially the same trend line fitting them. So coming up with a line, lines might not be the best type of function. Also, the trend line that Excel spits out might not be the best line that you want to use. So in these 2 concerns, in this case, it's all over the place. And what you could try to do, and it is possible, you can find a single function which goes through all of these points. But that would be, if I actually try to draw a little line here. So if you drew a line going through all of this, it's doing something like this, which is complicated, and this even doesn't go through all the points, but it's sort of all over the place. And so one reason why you might want a line is looking at this. Sure, the measurements are a little all over the place, but there's a pretty consistent angle at which the points are all going. So this line is not trying to exactly go through all these points, but you can say, okay, there's a lot of variation, but the variation is sort of all in this direction. So we won't be exactly right if we say this line is a model for our data, but this gives us the sort of broad scale behavior. We're going up at about this angle, and the actual points are bouncing around on either side of this line, but not too far on either side. So in this case, the line is really just a simplifying assumption. A function which exactly reproduces this has a lot of wobbling around, and we want something a little simpler. In this case, the line is fairly close to a lot of them, but also it's pretty clear that what we want isn't a line. This is a really distinct curve, and we can draw a single line that goes through them and is sort of nice, doesn't have a lot of bouncing around. And so while this is the line which minimizes the distance, we think if we take something curved like a parabola that comes from some equation or some function with x squared instead of just x, like a line, we can get a better approximation. In this third example, this is the line which best approximates all these points. But in this case, what you might think is, or if you have some reason for believing this, if you take the line going through just this, so all but one point looks like it's exactly on a line. Here's one outlier. And so you might have a reason for saying, this is the line which minimizes the distance, but I know that this was an extreme outlier and is not really going to be indicative of what's happening in the future. All these other points are more typical years, and those are what I should expect. So while the trend line is angled more than this series of dots, you might think, or you might have reason for believing, let's just take a line going through all these dots. I'll chalk it up to this was a outlier year. I'm not going to worry about it. If I'm going to try to predict what's happening, I'm going to keep going at this line. And this last one is just another really extreme example of a very different looking bunch of points that gives us the same line. So these are all to say, given some points, you can find a line which best approximates them, but given that, there's some understanding which is needed to think, is this really the best line for what my purposes are? So this is kind of saying, you can have this technology which can create this line for you. If you have the data, you can plug it into your spreadsheet and make the line, but it takes some human interpretation and understanding to decide if that line you want is really the best model for what you're trying to do. And we went over, and these give us, we talked about using these pictures, a couple of cases where the line might not actually be the best thing that you want. And so one way of dealing with this question, is a line what you really want, is that given a single set of data, we can find other types of curves that go through these lines. So in here, what we've been doing was I clicked on this trend line to make it show up. What you can also do is chart design, add chart element, and trend line, more trend line options gets you this little menu over here. There are all of these other types of functions. And if we look at some examples, so here, this curve is a polynomial, all these powers of x with their constants of order 2. 2 is the biggest power here. And while we maybe didn't notice it, we're above these lines and then below this one. And that, it turns out, really says that we are fit better if our line is curved. What we can also do is we can have an exponential function. So that's this first example right here. Exponential means it is looks like something y equals a times some number b raised to a constant times the variable. So in this case, what's happening and what is different is when we're talking about polynomials, the variable is being raised to different powers. So here, not raised to a power at all, raised to the second power, you could raise it to higher powers. In this case, the variable is up in the exponent. And so we're taking a fixed number and raising it to higher and higher powers. And so this is an exponential function. The base here is an irrational number e that looks like 2.71828. And looking at these different r squared values, we started with 0.98, that's pretty good. 0.9993, that's really good, but then it turns out that the exponential one is 0.9996. And these two is, I think, really hard to tell the difference. They're both so good that maybe it's this point is a little low here and it goes through it a little bit more, but still they're really good. So kind of distinguishing between these two, if you're trying to decide what is the better model, the R squared this is a tiny bit bigger, but close enough to not really make a difference. The decision would have to be which one of these kind of best represents what, or what we'll have to think about bigger properties than just do they go through the right points. And so we can look at some graphs of these to see what they actually look like. What I also want to point out is if we keep increasing the power, we can fit the line better. So in this case, in fact, if we go up from this 2 to the power 3, we get an R squared of 1, which means we exactly go through all 4 of these points. And you can always do this. Given any finite number of points, you can find a polynomial with a big enough order, a big enough largest power to exactly go through all of those points. And it turns out that if you have some number of points, the power has to be 1 smaller than that. So 4 points, we need a power of 3. I want to say, yeah, okay. So let's work out an example, again, going through the whole process. But also, in this case, we'll see that we really do have some considerations. And if we look at the graph, the larger graphs than just the part going through the points, what we'll see is that there are really better choices than others. So let's highlight our table there to make a chart, XY scatter plot. Here, we have a little more going on. Let's label these points because that's kind of nice to see what values we actually have. Then let's add trend line, just the linear one, and let's get the equation in the R squared. Make it bigger. Let's do double that. Okay. So we can make the linear approximation for this. And as you can see from the graph, the line sort of goes right down the middle, but isn't really very good. This R squared is pretty bad. Some of these other examples, 0.996, this is off by, so it's 10 thousandths, 4 10,000ths. That's super close to 1. This is less than 0.1. So this is really low, which is understandable. We have all these points around here, and our line just kind of trying to be close to all of them essentially goes right down the middle and isn't very good. So this is a case where a line is pretty clearly not the place that we want to go. While we're at it, also the exponential function is not very good either. A little better because it gives you some curve, which you sometimes want. But in this case, you can't really tell it's a curve. So exponential is also not the way we want to go. If you want a lot of kind of significant bend, you really need the polynomial. And right away, this polynomial of order 2, this quadratic polynomial, quad-like square, does a much better job. So having access to these different types of functions is really important. What's also important is to kind of think about what you're trying to model here. So for instance, if this is number of people in a hospital during a crisis such as ours, this is sort of a reasonable shape. It's going up, it gets pretty high, and then after the peak, it goes down. And so if we look at what is happening here, that's another class. I want this one. Okay. Oops, sorry. Translate it over. This needs to be, I'm going to change that to x squared. Okay, that's what I was missing. So that part of the graph, this is the whole graph of the function. We were looking at the kind of tiny part going from 0 to 8. Here, the horizontal axis is more spread out, so it looks a lot flatter, but it is the same function. From 0 to 8, we're looking at this part right here. So if you're thinking about wanting to model number of people in a hospital, this is a reasonable shape. At 0, you have some number of people. When we're talking about lines, the value at 0 is sort of our initial measurement. And then it goes up in peaks, and then it goes down, and at some point it's 0. And then we stop because we don't have negative people in a hospital. So looking at the shape of this graph, it kind of does what we want. Even though its R is a little below 0.9, that's still pretty good. But what I want to compare this with is if we raise the power up. So here, this gives us an x cubed term. And now our R squared is 0.94. So it's able to fit these a little better, and then kind of a harder curve down here than the parabola did. But if we look at the bigger picture of this, so it does a good job of fitting these, or better than the order 2 polynomial. So that is this one. So what we are seeing is from 0 to 8 on those points. So for this part from here over to here, they do track each other pretty well. But they are significantly different when you get to the other side of 0. So you have to really decide, does this difference affect the way I'm going to use this model? And going in the forwards direction, it is, so the blue one is the x cubed, the purple is the x squared. It fits it pretty well, and it does kind of the same thing. It goes up to some peak and then goes down, and is eventually 0. And after that, we definitely stop using it because we don't have negative people. But what we can also think is if we're using this model to start measuring at some time, we don't really care about the negative x's also. So the fact that they have different behavior, this is a region where the model just isn't doing anything for us. We don't care, we're not really worrying about a few days before we started measuring. So the fact that they're different means let's go with the one that fits our data better. So kind of what it's saying is that kind of interpreting the comparisons we can make, the blue line says we have a higher peak, it comes a little bit later, and we get to 0 a little faster. So those are some kind of practical differences that come from fitting those points a little bit, or using this blue polynomial to fit those points rather than the purple polynomial. But we can kick this up even more. If we say, let's take this and go to order 4, then we have a bigger power. We fit things even better. But in this case, we really see that this, maybe it fits better, but it's not exactly what we want to see. Or maybe it is, but we'll have to think more critically about it. So if we graph that polynomial, what we see is, again, during this 0 to 8 part, they track pretty closely because they're both trying to fit these data points. But then we see what happens, and we kind of saw that in the Excel version, is that we have it going up and then down, but this x to the 4th function goes way up, or it starts going up again. And we see that here. We see the bottom of the dip, and then it's starting to go up. And in this case, the decision that I think you would make is, sure, this function fits these points better, and its r squared is higher than, so in here, with order 4, we have 0.97. If we go down, we get 0.94. So this function fits these points better, but we have some idea of what is going to happen, or how we think things are going to happen. And that doesn't mean that things are going back up. Or maybe it does. Maybe the fact that this fits better is saying, is there reason to expect an uptick? After this initial peak, we start to drop. Is there a reason to expect things to go up again? Because this model is saying that it is. But just because a model says something, you have to understand the sort of limitations. Really, it's that polynomials of this form, they have certain behavior as you go off to the left and right. And in this case, an x to the 4th with a positive number multiplied, it's going to go up to the left and right. And it emphasizes a point that we talked about a little earlier. If we make this order 5, so there are 6 points. If we have an order 5 polynomial, we can go through them exactly. And we see that with its r squared is 1. this is what could be called overfitting, which means you choose your model with the only thing being, I need to fit the points that I'm given. I need to fit the data exactly. And realistically, you don't need to fit them exactly because there could be some error collection. There might be missing data. What is more important is closely approximate, but also fit your other assumptions of what the situation you're modeling actually, like what's actually going on. So in this case, sure, you can fit it perfectly with this order 5 thing, but this is sort of unhelpful, or you could consider unhelpful, because why is this peak here? What reason do we have for that? Why do we dip all the way down here? These are just things that happen in the polynomial in order to make it go through all these points. And you might say, what happens if you keep going up? Nothing happens, because if you already go through all the points, you can't really approximate better than that. And the higher order, in quotes, polynomials are saying you have an x to the 6th term, but multiply it by 0. So once you fit things exactly, you stop getting new stuff if you keep raising the order. So before I kind of connect to a real example that I found, do you guys have any questions about the sort of pictures that we've been looking at? Okay. So I'd say the basic skill that some homework problems will check is just, can you make a graph like this? And make graphs of different types. But the kind of more advanced skill that we were starting to talk about is, you can, given a model, how do you sort of interpret it, and how do you decide which one is better? Because we can make tons of different models. This moving average, we didn't even talk about what that is. We're not going to, but it's just another different kind of thing. And there are tons of different ways of making models, but there has to be a decision. You have all of these different functions at the buffet. Which one is actually the best? And it's not just which one goes through the points that you're given. As an interesting example of this, so as I was saying, there are other things besides just matching the data points. And kind of what you're considering is, in trying to just match those points, you need to think about, you're picking a type of function, and what are some other things to keep in mind? So as an example, if you know, in quotes, your quantity is growing linearly, then you maybe want to use a line, even if giving it some curve might fit the data points better. So that is maybe the situation in this picture here. You could draw a curve which goes through all these points. You could pick a polynomial, say, with a big enough power that it's super curvy and just hits all these points. But that is maybe overfitting the data, where what you really want to say is, chalk this up to a little bit of measurement area, or just sort of naturally occurring variability. The pretty clear trend is we're moving in this direction. And so if we assume that we're actually on the line, we maybe have to introduce some or worry about some error on either side, but maybe you can, error you can tolerate, or maybe even error that you can predict. Something like, we're going to be on this line, but we could be off by 5 in either direction. So give yourself a range that says we're roughly on this line, but a little bit on either side. So that's a kind of compromise. That's, talking about different kinds of error is another way of dealing with uncertainty in models. But what I thought was interesting was in the Twitter I look at is maybe different than any Twitter you look at if you use Twitter. But through my wife and some people I've met through her, I happen to follow some people that are biologists that actually do modeling for a living. And I found this kind of interesting thread that I thought I would share with you. And so the link is there in the slides, but this kind of gets at, you need to care about what function you're using, because that's where some assumptions might be able to slip in. So there was a model for number of US deaths or healthcare demand, like number of people in the hospital, people in the ICU, things like that. And the general picture is there's a steep increase and then a kind of slow decline afterwards. So definitely much steeper over here, which is earlier in time, as compared to later. But what this person noticed was, looking at some other models, they don't seem to fit, or there's a notable difference in that. So this, so these are the like actual variations. So they're still kind of going up, and the prediction is that they're going up, they're peaking, and then they go down. So this dotted line is the same in all of them. So this is Washington. It has its peak a little bit ago. This New York peak happened before that. This California peak happened afterwards. So it's different data, but what was noticed about all of these is that these are very symmetric. They're going up, and in the same kind of way they're going down, as compared to this projection, which was much steeper on this side and then a slower decline on the other side. And great. So okay. So there's some more here, but I'll just kind of summarize it. So the kind of, what you might think is, this one is maybe more realistic. Thinking about what's actually happening is, a lot is happening all at once. And then as things get under control, either social distancing is taking more effect, or people are recovering, and recovered, they're hopefully immune. And so there are fewer people around to infect and transmit. On the other side, things get better, but not in a really quick way. There are still people getting sick and people are recovering, but it's a slow process to recover. And as people are recovering, people are getting sick. So on the backside is a much slower return down to the kind of baseline level than it was increasing to the worst of it. And in these symmetrical pictures, that sort of two sides, it's bad before the peak, but then slowly gets better after the peak, isn't happening. And so the question is, there's an acceleration before and then a slow deceleration after, once kind of mitigation methods are in place. Why were these symmetric things showing up when it's clearly not a symmetric situation? And the answer is that the type of function that they used, which is a big mess, don't worry about this. They use a kind of function. Here's the point. The form of the curve they used forces everything to be symmetric. So they had some data, they tried to model it, but even though the situation realistically is not symmetric, the type of function they used made their models be symmetric no matter what. And so that's a problem. If you know sort of externally that there is a significant asymmetry between the ramp up to the peak and then the aftermath of the peak, you don't want to use something which is symmetric. And so there's some other pictures here where they actually have some of these predictions. So this is what they actually were measuring. And then these are kind of various predictions at different times. And all of these predictions are symmetric. But what's happening, and I think this picture shows that, well, that's a really unfortunately placed thing here, that they have what's actually happening, they have the projected track, and then they have it zeroing out at some point. And why that is kind of unrealistic, goes on to explain here. Let's see. Does he explain here? No. Okay. So kind of what I think he explained in here, I can't find it right now, is this model predicts the disease to die out quickly, but that is unrealistic because the model is only predicting it to die out quickly because things have to be symmetric. And if something gets big quick and you're symmetric, you have to get small quick also to match, to be symmetric on two sides of the peak here. And so that's a kind of dangerous inference to make if the only reason you're doing it is because you're using something which is forced to be symmetric. Right, so there's a lot of other stuff here, but I wanted to look at a right, so here's kind of the line. Pre-controls expansion, so things get bad quickly. After we've put in some mitigation controls, things get better, but they don't happen at the same speed. And assuming they do is a flaw in reasoning. And so just to kind of see what's happening there is the basic form of the function they're using is something like this. And this is kind of good. It goes up to a peak and then it goes down. What they're doing is something more like this function, where what is happening here is, and maybe you remember this from a previous math class, but the effect of multiplying by 50 stretches it out. This -10 in here shifts it over 10 units. So you can have a basic shape and kind of shift and stretch it. But what their model is doing is something like this. Things grow really quickly, but then because this type of function is symmetric, it has to also decay really quickly. And realistically, that isn't going to happen it gets bad quick, but then is a much slower descent on the other side. So those are some things that are important to think about when you're, for people who are coming up with these models. You can have all sorts of model fitting software. Say, I want to hear some data. Let's find a function that looks like this, which fits it. But you have to think about more than just going through the points. There are other things to worry about. Okay. So next class, we're going to start, we're going to get away from looking at pictures. Maybe you like looking at pictures. I think it is good to get a little experience or like maybe insight into what do you think about critically when you're looking at all these different graphs. And there's a lot to think about if you're wondering where they come from. But we'll get back to talking more about using models to answer some questions. And then also get into exponential models, which are common in population sizes, or I guess, populations either growing or populations of sick people growing or changing. And so we'll talk about those in a sort of similar method that we were talking about with linear models. Okay, but then